So one of the questions I've got from students is about the the line structures, determining the molecular geometries and electron domain geometries when you are given line structures. Okay, so I'm gonna make a short video here to and give you some examples of how to tackle a problem like that. Okay, so let's consider something like this. So here that we have this molecule. Then to this we have a hypothetical molecule, okay? Oxygen bound to this, and also molecule like this. Okay. Now what I'm going to do is I'm going to pick 3 atoms from here, okay, and I'm going to determine the molecular geometry around them. This is atom 1, atom 2, atom 3. Okay, let's make it atom 4 as well. Atom 4. Okay, whenever you are given a problem like this, the first thing you need to do is convert this structure to a Lewis structure. Okay, so here's the easiest way to do this. I'm gonna draw it in a different way now. Okay, I'm gonna redraw the line structure. Okay, so here's my this benzene ring here. Okay, and here are my double bonds, and then this oxygen atom. This nitrogen containing group. Okay, so I just redrew my my line structure. Then what I'm going to do is I'm going to replace my ends and bends with carbon atoms. Okay, so do it now. Here's a bend, the carbon. The bend should be a carbon. It's another carbon. It's another carbon. It's another end. Carbon. It's another bend. It should be a carbon. And then it's another one. Carbon. 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 And carbon. Okay, and then what I need to do is I need to fulfill the common bonding pattern of these carbons by adding carbon hydrogen bonds. Okay, this one do now. So now let's start with this atom over here. Because this atom over here at the top. So I have 1, 2, 3 bonds around this carbon now. Every carbon, so it needs to have 4 bonds to fulfill the common bonding pattern. So I'm going to add a carbon hydrogen bond. Okay, same thing here. Only 3 bonds right now. 4th bond should be a carbon hydrogen bond. Okay, so I'm going to keep doing this. The carbon hydrogen bond, carbon hydrogen bond. Okay, and this carbon over here already has 1, 2, 3, 4 bonds around it, so it is okay as it is. And this carbon has only 3 bonds, so I'm going to need another carbon hydrogen bond. Okay, and this carbon has only 2 bonds, so I'm going to need 2 carbon hydrogen bonds. Okay, same thing here. We need 2 carbon hydrogen bonds. Okay, and the same thing here. 2 carbon hydrogen bonds. Oh. Oh, hard to draw here now. Okay, two, and then in this carbon, I only have one bond, therefore I'm going to need 3 carbon hydrogen bonds. One, two, and three. Okay, that's the first thing I would do. Okay, take a little bit of time and then draw the Lewis structure of the compound. Okay, and then that is useful. That is actually needed. For example, if you have to find the molecular formula of this compound. Okay, so in the molecular formula of this compound, we have carbons, we have hydrogens, we have uh, uh, nitrogens, and we have oxygens. Okay, and then if you count the number of hydrogens, carbons first. Okay, you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 carbons. Okay, let's count again. 6, 6 plus 5. So when it comes to hydrogen, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 hydrogens. When it comes to nitrogens, only 1 and 1 oxygen. Therefore, this should be the molecular formula of this compound. Okay, without drawing out these carbon hydrogens, without converting this line structure to a Lewis structure, you cannot determine the molecular formula properly. Okay, that's part of it. Now, what we want to do is we want to determine the electron domain geometries and molecular geometries around each of these atoms 1, 2, 3, and 4. Okay, so let's start with that. Okay, we want the electron domain geometry and the molecular geometry. Right, the molecular geometry. Okay, let's start with atom 1. Okay, atom 1 is okay. Atom 1 is over here. This is 1. This is 2. This is 3, and this is 4. Okay, one other thing actually I should, before I forget, I need to mention, it's really important that you indicate the lone pairs in the Lewis structure. Okay, so for an example, in this oxygen over here, we only have 2 bonding electron pairs, so we're going to need 2 lone pairs to fulfill the octet. And nitrogen here has already 3 bonds around it. That means 3 times 2, 6 electrons. So we're going to need okay, that we're going to need 1 lone pair to fulfill the octet around that nitrogen. Just keep that in mind. Okay. Now going back to the geometries now. 1 has 1, 2, 3 electron domains around it. Okay. A single bond is an electron domain, a double bond is electron domain, or the single bond of carbon hydrogen is electron domain. Therefore, we have altogether 3 electron domains. If you have 3 electron domains, they arrange in a trigonal planar geometry to minimize repulsions between them. So let me see if I can write trigonal planar here. Okay. It's gonna be trigonal plane. Okay, so I'm gonna TP within parentheses here so that I never have to write this again. I can just write TP rather than the entire thing. Okay, anyway, trigonal plane. And then the electron domain geometry is trigonal planar, and all of these electron domains are bonding electron domains. Okay, therefore the molecular geometry is also trigonal planar. TP. I wrote TP here instead of writing the entire thing now. Trigonal plane. Okay, going to attempt 2. Attempt 2 is this oxygen over here. I have 1, 2 bonding electron domains, and then I have 2 lone pairs. So altogether I have 4 electron domains. Whenever I have 4 electron domains, the electron domain, the geometry must be, electron domain geometry must be tetrahedral. Okay, so I'm going to write tetrahedral here. Okay, so electron domain geometry is tetrahedral because we have 4 electron domains around this oxygen atom. And then when it comes to the molecular geometry, we only concentrate on the bonding electron domains. Okay, we have 4 electron domains, but only 2 of them are bonding. Okay, and then you can see that they are in an angle. Okay, so that is called a bent geometry. That's too large. Come back to that. Okay, so the molecular geometry around that oxygen is bent. Okay, and okay, for tetrahedral, I'm going to have TH so that if I have uses in the future, I can write TH instead of writing the entire thing tetrahedral. Okay, anyway, so that is atom 2. Moving on to atom 3, which is our nitrogen atom over here. Right, it's nitrogen atom over here. Again, you have 3 bonding electron domains and then 1 lone pair. That means altogether we have 4 electron domains. Whenever we have 4 electron domains, we know that the electron domain geometry is tetrahedral. I'm going to write TH for tetrahedral. And then when it comes to the molecular geometry, we only look at the bonding electron domains. Okay, with rest, arrangement of the bonding electron domains in this space. So they are arranged in a trigonal pyramidal geometry. Okay, so trigonal pyramidal. So I'll write that down here. So the molecular geometry around the nitrogen atom is trigonal pyramidal. Okay, that is atom 3. Now moving on to atom 4, which is this carbon over here. Okay, so that carbon has 4 electron domains around it because we have 1, 2, 3, 4 single bonds. Okay, every single bond is an electron domain. Therefore, the electron domain geometry is tetrahedral. Okay, and then all of these electron domains are bonding electron domains. Therefore, the molecular geometry is also tetrahedral. Okay, a common mistake students do is they just look at the line structure over here. Okay, you can see at 4 we just have this bent structure. Okay, bent structure. Okay, but it is not actually bent. Okay, you know this bend is a carbon atom. Okay, and then we fulfill the common bonding pattern of the carbon by adding carbon hydrogen bonds. Therefore, it's going to be a tetrahedral geometry, both electron domain and molecular geometry, not bent. Okay, so the bottom line is whenever you are given line structures and asked to find geometries, molecular geometries or electron domain geometries around these atoms, you need to draw the Lewis structure before you determine these geometries. Okay, I hope this video helped you